Welcome to This Explainer. You know, we talk a lot about AI models and software, but if you ever stop to wonder what the physical brain of the AI revolution actually looks like, well, today, our goal is to take something incredibly abstract and complex, NVIDIA's back-end networking infrastructure, and break it down into a highly accessible, logical blueprint. We're going to decode the exact architecture that powers this modern AI boom, looking specifically at how all these discrete components wire together. All right, let's just jump right in by grounding this highly abstract topic in a really tangible metaphor. When we look at modern data centers, we aren't just looking at servers anymore. We are touring a factory. This is an AI factory, and its sole product, its manufacturing output, if you will, is tokens. We're talking about building a massive single unit of computing that just happens to be made up of thousands of interconnected pieces working together. And here's the absolute crucial takeaway right off the bat. Off-the-shelf parts? They simply won't cut it. As this quote highlights, creating this single unit of computing requires an extreme co-design. Every single piece of compute, networking, and storage must be custom-fitted and perfectly synchronized to work in total unison.
So here is our roadmap for today. 1. Scale up inside the rack. 2. Scale out across the data center. 3. Context memory for AI storage. 4. Scale across remote sites. 5. NVLink fusion. And finally, 6. Digital twins. Let's get into it.
Step 1. Scale up. Building one giant GPU. Let's head right down to the factory floor. The core mission here is to connect multiple chips via NVLink so tightly that they literally act as one massive GPU. And this brilliantly illustrates how physical design choices dictate computing power. See, when you're building out this rack, power is your main limiting factor. Every single watt you save on cooling or data transfer is a watt you can pump right back into the GPU to generate more tokens. So they keep the connections within the rack on copper wiring, which uses way less power than optical cables. They use hot liquid cooling to avoid those power-wasting chillers, and they actually handle data reductions directly on the switch fabric itself so the GPUs don't waste their precious compute cycles just shuffling data around. It keeps all the power consumption strictly focused on actual computation. And NVLink, well, it isn't just a traditional network. It acts as an actual extension of the GPU itself. By moving calculations into the network, it provides 130 teraflops of in-network compute. I mean, that is an astronomical number of calculations per second happening directly inside the network wires themselves. Because of these massive efficiencies and extreme low latency, we're seeing a 2x performance improvement on different AI workloads right there at the rack level.
Moving on to Section 2, Scale Out. Jitter-free networking.
Now we need to zoom out a bit. To build a true AI factory, we have to connect hundreds of thousands of GPUs together, which means tackling the biggest enemy of distributed computing, jitter. Traditional off-the-shelf Ethernet acts as a total bottleneck for AI. It was built for single servers getting data in and out, heavily relying on deep buffers, which naturally create performance-killing latency fluctuations or jitter. Spectrum X, on the other hand, is a purpose-built AI Ethernet. It uses a lossless RDMA architecture, meaning it bypasses the operating system entirely to ensure direct, zero-jitter memory access. This delivers constant, steady performance even when multiple jobs are running on the exact same infrastructure. So how do they completely avoid data traffic jams? The hardware uses this brilliant three-step adaptive routing process. First, the switch unconditionally blasts traffic across any available path. It doesn't get stuck waiting on a single congested route. Second, instead of using temporary buffers that just cause delays, a SuperNIC intercepts that scattered data and places it directly and perfectly in order right into the GPU's memory. Finally, a signal alerts the GPU that its data is fully ordered and ready to consume. It absolutely guarantees that data arrives seamlessly, keeping our factory lines moving fast. And the results of this extreme co-design? They're undeniable. By optimizing the Spectrum X hardware to work perfectly with their collective communication software, known as NCCL, they achieved up to a 14x performance boost on collective operations. Considering these operations make up about 80% of network traffic during pre-training, that is a monumental leap in factory efficiency. And as we scale out across the entire facility, we eventually have to start using optical networking, which historically eats up a massive amount of power. So, NVIDIA designed co-packaged optics, utilizing micromodulators right alongside the switches. This specialized packaging resulted in a staggering 5x power reduction for the optical network. Again, power saved here is power redirected to generating more AI tokens. Section 3. Context Memory. AI-specific storage. Look,
Generating AI requires pulling immense amounts of data instantly. The problem with traditional network storage is that it carries far too much overhead for rapid AI generation. It's built for safety and data protection, not pure, raw speed. So they utilize BlueField processors to create a brand new storage tier. This basically acts as a direct, high-speed highway from the GPU straight to the storage, bypassing all that unnecessary network baggage and maximizing token throughput.
Section 4. Scale across, connecting remote sites.
Zooming out even further now, sometimes power or space restrictions mean we have to split our compute capacity across remote sites. And this is where it gets really clever. Traditionally, long-distance data uses deep buffer switches as shock absorbers for the unpredictable journey. But draining those buffers adds 2 to 3 times the latency penalty of the physical distance itself. I mean, it makes absolutely no sense to pay a 3,000-mile latency penalty for a 1,000-mile distance. So instead, they use distance-aware algorithms. Hardware telemetry probes actively measure the exact latency to understand the distance and then dynamically adjust congestion control on the fly. By dynamically adjusting this load balancing based on that active distance telemetry, this approach nearly doubles the performance across remote data centers compared to using off-the-shelf deep buffer solutions. It effectively hides the latency penalty of scaling across regions, which means you get faster AI responses no matter where the servers are physically located.
Section 5. Building the ecosystem with NVLink Fusion.
Now you might be thinking, what if I'm a developer who wants to build my own custom chips? Well, NVIDIA actually built a bridge for exactly this, called NVLink Fusion. These chiplets allow any custom processing engine, any XPU, to seamlessly plug directly into this highly optimized supply chain. You can bring your own custom processor to the table, but still leverage the copper backplanes, the BlueField storage, and the Spectrum-X networking. It completely opens up the factory to the broader ecosystem.
And finally, Section 6. Digital twins, validating the factory.
Before a single physical rack is ever bolted to the floor, they build the entire thing virtually. Because when you're running an AI factory, any downtime means you aren't generating tokens, and that means you aren't generating revenue. The DSX Air digital twin turns what used to be months of risky physical testing into just a single week of totally safe simulation. You can configure switches, run routing protocols, and safely simulate firmware updates with literally zero physical downtime. Once the digital twin is running perfectly, you just copy the configuration straight over into the real physical design. As we step out of our tour of the AI factory today, it leaves us with a pretty provocative thought. We've seen the extreme co-design, the jitter-free networks, and the distance-aware telemetry, all optimized down to the absolute single watt to do one thing: generate tokens. But as these hyper-efficient data supply chains continue to scale and evolve, what boundless potential will they manufacture next? Thanks for joining me on this explainer today. I really hope this blueprint helps you see the true physical reality behind the AI revolution.